So, can you hear me? Okay. So, good afternoon, everyone. I'm MatteoImbrogno, last year PhD student at the Observatory in Rome. Thank you for having me here. And today I will talk to you about this project we are developing together with the Magnesia group at ICE in Barcelona. And since I'm very glad to work with those fantastic people, I will declare immediately that the only one to blame for having Antonio Banderas talking with a hand at the title slide is me. I'm the only one to blame. And if you're asking yourself, why is Antonio Banderas talking with a hand? Well, we can chat later about Italian television in the early 2000s. So a better title for this presentation would have been The Hunt for Variable Sources in eROSITA Data and Beyond, because as I will show you, this project started with eROSITA and eROS1, but we hope that this will become a tool that the community can use for a systematic and automatic search for interesting sources in the X-ray archives. And for interesting, we all work with, we are all interested in timing analysis in our group. So we mean sources showing like coherent signals or other kind of variabilities. How can I? Okay. So since Ibandera started with eROSITA, let me start real quick about eROSITA. We all know this satellite very well, thanks also to the talks of these days. So we all know that eROSITA is an imaging telescope that has been built with the precise scope of perform the most sensitive all-sky survey in the 0.2 to 2.3 keV bands. And of course, we expected to have a lot of sources, and X has shown us that there are a lot of serendipitous sources that hide interesting variable phenomena. And we were like, how can we exploit this data? And we also included in our search early data release observation. Here you can see, okay, here, this is a typical field of view of eROSITA of one of the early data release observation, where you can see that you have lots of serendipitous sources in the field of view. So you can, there's a lot of space for new interesting phenomena. But of course, eROSITA is very well known for its survey mode. It is the beautiful image that has been produced by eROSITA. And one of the striking features is the large number of sources that has been detected. And I just want to quickly remind you how eROSITA works with how the survey mode works, since, of course, while we keep the EDR data to search for coherent signals, in the case of survey observation, we are more interested in other kind of timing variability in the eROSITA data. eROSITA observe one great circle of the sky in about 4 hours, which is called also one eRO day, which means that each point in the sky, given the 1 degree field of view, is observed for about 40-second chunks with up to 6 chunks per day. And of course, sources nearer to the ecliptic poles have a longer total exposure at the end of the single survey. This is an image of the German sky divided in the sky tiles. This is how you can download data from the eROSITA archive. Of course, German sky, because as we all know very well, only half of the sky is available to us with the German sky, the right part here, while the Russian sky, the left part, is like basically those video games where you still haven't unlocked the regions in a map and you have this impenetrable fog where you don't know what is happening. Okay. So what impressed me is that although we only have half of the sky, eROS1 is already the largest X-ray catalog ever produced, with almost 1 million sources detected only in eROS1, and we can only expect this number to grow with the subsequent data release. And with XMM, we have lots of sources. So we are officially in an era where you have to think of a smart way to search for interesting signals, temporal variability in the data. And what we wanted to do was not only to start a project that would find interesting variable sources in the eROSITA only for the eROSITA data, but something that could last also for future missions that can be applied to other X-ray missions and even non-X-ray, as I will show you in a moment. So to to exploit this huge archive, that's where Banderas comes into play. This is just a quick flowchart of our own pipeline that we are producing. If you're asking yourself why we also wrote a script, as I will show you in a moment, to quickly perform the data reduction, since we are also interested in the early data release data. And here you can see all the type of temporal phenomenon that we are searching at the moment, passing through transient phenomena, burst, coherent signals in the case of early data release, of course. And so, as I said, this is a pipeline. This is a pipeline that we are writing in Python, of course. And the idea is to release it also at a certain point to the public to allow as many people as possible to perform data mining of these huge archives. So let me start with our two mission-dependent modules, since as DAXA, the talk about DAXA already showed, some things about the reduction, of course, depends on external software, which are mission-dependent. In the case of Eurosita, we have, of course, ESAs. We have written these two modules, error reduction and error body. Error reduction is basically a script that performs all the steps of the data reduction as outlined by the online cookbook, from the extraction of the events down to the production of the sources. Every module in this pipeline is written in such a way that it can be used in two different modes, pipeline and single source modes, we call it. In pipeline mode, error reduction basically perform all these steps for every single source detected in the field of view of Eurosita. While in single source, you can pass directly the coordinates, for example, from the Eurosita catalog, or if you are interested in a specific source. Eurobody is basically a wrapper of Bison, a biocentric tool that we started developing before eBison was released, but for the moment we're still keeping it. But I think that the real strength of what we are building is in the data analysis package, which are mission independent. We tested them on XMM data, Chandra data with data, they work very well. Regarding the search for coherent signal, let me show you a typical output of what we call DPS-Pi, which is basically the Python version of the Fortran tool that also Andrea De Luca showed you, that was used for in extras to search for coherent signals that generalize the detection threshold computation and the computation of the significance of the peak. In the case of the more general case of red noise, here it's not the perfect choice, but in the next slide, I will show you what I mean with a variable detection threshold, a frequency-dependent detection threshold. It relies upon Stingray to compute the power spectrum. I don't know if many of you work with Stingray. Timing analysis is a wonderful package for X-ray timing analysis. And this is an EDR observation of Eurosita of NGC 7793P13, passing ULX, as we have seen just a few moments ago. You can see here that in case of a peak detection, we have, of course, here you can see the peak, the power spectrum, and here in blue, you can see the frequency-dependent detection threshold. We tested this also for some optical data, since we're also involved in analysis of TNG and GTC data, and this is very fast also with optical data, so you can use it with your mission of choice, basically. Of course, you don't always detect a signal in your source. In this case, here you can see, this is another EDR observation of Eurosita of 472 globular cluster. In this source, there's no signal detected. Here you can see that in the presence of red noise, the detection threshold at 3.5 sigma evolved with the frequency. In this case, DPS-Pi produces two plots, one with the power spectrum, the other one also with an upper limit of the pulse fraction. This will change in a future version, since it is not very clear, but here the scale is in pulse fraction from 0 to 1. To have an idea of where is the upper limit on the pulse fraction of a potential signal. So this is what we have done regarding the search for coherent signals in Eurosita and also other X-ray emissions. While let me introduce you now to our aperiodic variability search tool, which is Avenue, which is basically a standalone pipeline. It looks for other kinds of variability. This is more useful for Eurosita data where you have all the gaps. Unfortunately, the colors you don't see very well, but here you can see this light curve of a source in an Eurosita sky tile. This tool, it basically performs a large number of checks to verify the presence of aperiodic variability in data and to have a quick look of as many sources as possible in the field of view. Samples the time series. This is all configurable by the user, and so you can change how you want to beam the data, how many, which is the signal to noise ratio, the minimum signal noise ratio that you want, the minimum number of counts. Thank you. It computes Bayesian blocks, a power spectrum, and one thing that it also introduced, it also fits with Gaussian mixture models, the count rate distribution. This was thought because most people in our groups, I will show you better in the next slide. Most people in our groups are interested in the study of transitional milliseconds pulsar and the search for new candidates, and they are characterized by transitional millisecond pulsar are characterized by the presence of low and high modes in the light curves. So they can be possible candidates can be found by the presence of this bimodality in the count rate distribution. And we wanted to introduce this tool to have a way to assess new possible candidates in the archive, even for those missions that don't have the actual time resolution to detect millisecond pulsar, like for example, Eurosita with a time resolution of 50 milliseconds. And you can see that the tool also performs a Bayesian blocks analysis. I don't show here because it will be too long, but it also prints a large number of values by excess variance and similar that allows the user to quickly check if the source is really interesting or not for the kind of analysis they want. Of course, we also implemented this tool, which is an HR, which computes which study the aperiodic variability of the light curve as a function of the energy. Or even in this case, the user can choose how to rebeam the soft and hard band light curves. They can choose the energy at which they want to define soft and hard bands. It computes also an hardness intensity diagram, which with the evolution in time to verify if there is an evolution in the light curve in the properties of the source. And there are also many other packages that we want to introduce that will hopefully help people to perform their own data mining analysis of huge archives. For example, we are working on a match package that a match module that cross-match the position of the detected source with other X-ray and known catalogs. We want to extend our analysis to spectral variability with PIC-C, a PI-spec-based module for systematic automatic spectral analysis for as many sources as possible. We're trying other algorithm, non-FFT-based algorithm for the search of coherent signals. And we are trying to implement something similar to extras for the search of bursts and transients in the archives. So, okay. So this is just a summary of my tool. What I really want to highlight is that, yeah, this work, the Ibandera is just the beginning, since, yeah, our long-term goal is to provide to the community a tool that can really help to perform this kind of systematic automatic search for variability. So long. Thanks for the pitch. And I'm here for your questions.
Thank you for this very interesting talk. We have a question at the back. I think it's Axel, but I'm not sure from here. Yes.
My name is Axel Schwope. Still. One comment, if you perform FFTs or things like that on Eurosita data, there's a clock drift. You probably find a wrong period if you're looking for short period systems, for short period time variability. If you would like to know the nitty-gritty details, I can give you a reference.
Okay, yeah, thank you. And as I said, The FFT is just one of the possibility. We're also thinking of other algorithms to work in parallel. Yeah, if you can send me, yeah, that would be very useful. But yeah, we are keeping all the possibilities so that everyone can choose according to the mission what is the best option, let's say.
Some other questions at the back? Is there anything on Zoom? Okay, I actually had a couple of questions, so that worked out very well. Thank you. So are you trying to use accelerated searches as well? So you talked about 47 Tuck, for instance, as that you pointed.
Not yet. This is something we want to implement in our search. But yeah, with Stingray, it's quite easy because there are some tools that already do that. So at this moment, we are not asking how to do that, but for which sources, because yeah, we have 1 million sources, but for most of them, let me just go back to this slide. For most of them, you have like 10 counts, and it doesn't make sense to perform accelerated search. So we will probably use that only for sources with at least 100 or more counts. In the case of Erosita, then for no, in general, yeah.
Yeah, actually, that was my next second point, actually. Thank you. So yeah, you showed some power spectra, but they were obviously clearly not from Erosita, I presume.
No, sorry, maybe I wasn't clear enough. These two observations, this is just to show that these tools also works with other observations. These are two XMM observations. These are from XMM. Yeah, sorry.
Okay, that makes it more clear to me.
No,
thanks.
sorry.
Okay, so if there's nothing more for now, let's break for some more coffee, and we come back at 4 o'clock.